Welcome back. In this video, we're going to talk about the heat of combustion. Now, this topic is very common in the exam, and it's really important that you can define the heat of combustion, but also write different combustion equations. So, in terms of the exam, you need to be able to do three things. Number one, give the definition for heat of combustion for 6 marks. Number two, write equations for the combustion of common hydrocarbons and technically alcohols as well. And number three, describe how the bomb calorimeter works. The bomb calorimeter is something that hasn't come up in a very long time. And it's just something that's sticking out that could be a really tricky question if it came up in the exam. So I am going to cover it here, and I am aware that some teachers do skip this. So if your teacher skipped this, I would recommend that you still follow along with the bomb calorimeter and be able to tell me how it works on the off chance that you get asked it in this year's exam. Right, so the definition for heat of combustion. So previously, when we went through the definitions, I mentioned heat of reaction, heat of combustion, heat of formation, and heat of neutralization. And your first 3 marks always come from the heat change. Your second 3 marks are for telling me that it's 1 mole of a substance is completely burned in excess oxygen. Now, the part of this that I really need you to fixate on is the phrase 1 mole, because not all reactions based on balanced equations are the reaction of 1 mole with oxygen. And we will see that that will be very important when it comes to the calculations, that you can figure out what's the difference. So let's have a look. So what does that actually mean? If we take something that is combusting, say for example a hydrocarbon, or if I was to take methane. So if I take methane, which is CH4, and react it in excess oxygen, which is O2, that ensures that all of your hydrocarbon burns to form carbon dioxide plus water. If your oxygen is not in excess, it means you would form carbon monoxide instead, which is highly toxic and very dangerous. Now for this reaction, I'm going to put a 2 in front of the water, and I'm going to put a 2 in front of the oxygen to balance. Now, during this reaction, we have to break apart the bonds in the methane and oxygen, and then we form bonds in carbon dioxide and water. Now, from this balanced equation, let's look at the numbers in front. 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of H2O. Now, this particular reaction will have a very specific delta H. It has a very specific energy change for this reaction, and it will be a negative symbol. Now remember, as soon as you see a negative value for delta H, you know it's going to be an exothermic reaction. All combustion reactions are exothermic. This is actually the reaction that happens in your house when you burn methane, which is what natural gas is. You have a spark in a boiler, and that provides the initial spark, the initial source of energy that's needed to get the reaction going. And then the methane reacts with oxygen to give us carbon dioxide and water, which is then goes out through the exhaust pipe. If this wasn't an exothermic reaction, there'd be no reason why you do this at home. Exothermic reactions release heat to the surroundings. So when we do this reaction in a boiler in your house with natural gas, then you are releasing heat, and that's what's actually then being used to heat your house. Same for if you have a natural gas cooker at home. You ignite the methane, and then the heat released as the methane is burning is going to be used to cook food. So all combustion reactions are exothermic, and it doesn't matter what the thing is that is combusting. They will all have their own individual unique delta H values, but it is specific to that particular reaction, but they will all have a negative sign. If I was to come along and pick something different, like propene. Now, propene, if we look at the formula for propene, prop tells me it's going to have 3 carbon atoms, so it'll be C3. And ENE tells me it's going to be an alkene, which means it will have the formula C3H6. Remember, alkenes have the general formula CnH2n. So you have twice as many hydrogens as you do carbons. If I was writing the equation for the combustion of propene, we would have C3H6 plus oxygen to give me carbon dioxide plus water. Now here, to balance, I need to put a 3 in front of the CO2, I need to put a 3 in front of the water, and I have to put 4.5 in front of the oxygen. Now, I haven't looked up what the heat released for a propene reaction is, so I'm going to cheat a little bit and I'm going to make it up. So nobody go look this up and go, well, it's actually minus 500. No, I'm just making it up. So I'm going to put it in as minus 1,000 kilojoules. Now, when that particular reaction happens, 1,000 kilojoules of energy will be released. Now, let's look at our molar ratios. When 1 mole of propene reacts with 4.5 moles of oxygen, and we form 3 moles of carbon dioxide and 3 moles of water. This is the amount of energy that is released for that particular reaction. Now, if we look at that balanced equation, the delta H here, a lot of people get confused and think delta H definitely means heat of combustion. It can and it can't. It depends on the reaction and what the information is that you're given. Now remember, with heat of reaction, and from the definition for heat of reaction, this is dependent on the balanced equation that you are given in the question, and the number of moles of each substance in the balanced equation. Whereas with heat of combustion, that is specific to 1 mole of something reacting. So it's 1 mole of methane. Now, in this case, for this particular example, for the propene reacting, heat of reaction and heat of combustion are the same. So this delta H that we've calculated over there on the right-hand side is the heat of reaction. And it is also the heat of combustion. It is the same in this particular case. Now, I know that a lot of you don't like fractions and decimals when you're balancing, so I'm going to get rid of the numbers in front. That's not going to get rid of it for me, so let's move this up. So I have C3H6 plus O2 to give me CO2 plus H2O. If I was to multiply across by 2, that gets rid of the fraction. So now here, that will be 2 propenes reacting with 9 oxygens to give me 6 carbon dioxides and 6 water molecules. Now, it is balanced, so you should have 18 oxygens we do, 6 carbons and 12 hydrogens, which is perfect. Now here, the delta H for this reaction, as it's written, would be minus 2,000. Now, it has to be twice as big because you are breaking twice as many bonds and forming twice as much product. So here, you have 2 moles of propene reacting with 9 moles of oxygen to give me 6 moles of CO2 and 6 moles of water. Now here, the delta H that's written on the right-hand side, that represents the heat of reaction because it's based on the balanced equation that's given in the question, but it is not the heat of combustion. In this case, this is for the combustion of 2 moles of propene. If I wanted to say what the heat of combustion was, I would need the energy released for 1 mole of propene. And in this case, you would take your minus 2,000 and divide by the number in front of the propene in the question. So you would be dividing by 2. And that will get me the amount of energy released by 1 mole of propene. So that is your heat of combustion. So whether or not your heat of combustion and heat of reaction are the same, it depends on the balanced equation. If it's 1 mole of something combusting, then yes, the heat of reaction and heat of combustion is the same. But as soon as you see a number in front of the thing combusting, well then it's no longer the same thing. Now you have to understand that because when it comes to the calculation, you could be asked to calculate the heat of reaction or the heat of combustion. And I love a good tricky question. I've put it on my mock papers the last few years where I've given students like 2 moles of something combusting, but then I've asked them to work out the heat of reaction. And what I'm doing with that is I'm testing to see who understands that heat of reaction means use the balanced equation only and heat of combustion would be you divide by the number in front in the balanced equation. Now we're going to see this again in a little bit when it comes to doing the thermochemistry calculations. Now I will say 9 times out of 10 when you're working out, it will say calculate the heat of reaction, but it will be for 1 mole is combusting in the equation. So the heat of reaction and the heat of combustion can be considered the same thing. It depends on the balanced equation though. So now, my next step. So I just wrote the balanced equation for 2 combustion reactions. Now you have to be able to write these balanced equations for yourself. So the exam tip that I've put in your notes is I've tried to make it relevant to something that you might have seen already in biology or junior cycle biology, which is respiration. Now respiration, the process of taking in glucose and using oxygen and converting it into carbon dioxide and water and the release of energy. Respiration is an example of a combustion reaction and energy is released and we use that energy then. When you are writing the balanced equation for the combustion of a hydrocarbon, I strongly recommend that you write the equation for respiration first on the exam paper, because that's going to then act as a scaffold for the rest of the balanced equation. But then just make sure you rub out or cross out C6H12O6 and write in what the actual hydrocarbon is. Now, when you're doing it that way, make sure you put a line through your respiration question or your respiration answer. If your examiner sees 2 balanced equations on your answer booklet, cancellation applies because you've given them 2 answers and you haven't said which is right and which is not. So always put a line through it and then they'll use the other answer. We're just using this to scaffold our answer. It's not going to be getting us marks in the exam. Right, so our balanced equation for respiration. Let's have a look. Actually, let's write it down here at the bottom. So in this space down here, I'm just going to move that out of my way. Let's start off with glucose. So for respiration, we have glucose reacts with oxygen and we form carbon dioxide plus water. Now, glucose has the formula C6H12O6. The formula for oxygen is O2, and then we form carbon dioxide plus water. Now, I'm not going to balance this for glucose because I won't have to do that in the exam. They're not going to ask you for the formula for respiration, unfortunately. So I'm not going to take this any further. But I now want you to use that as a scaffold for if your examiner asked you for, instead of glucose, they wanted the combustion of, let's move this down a tiny bit so I can do a little bit of working on the top. If they wanted you to write the formula for the combustion of ethane. Now, ethane, eth or eth, that is 2 carbon atoms. So that's going to be C2. It ends in ane, which is an alkane. Alkanes have the general formula CnH2n plus 2. So to work out my number of hydrogens for ethane, it's 2 times 2 is 4 plus 2 is 6. So it's C2H6. I know a lot of students actually prefer to do that. They draw out the structure of ethane and then count the number of atoms, which you absolutely can do. It is the same thing. I don't care how you work out your number of atoms of each element, as long as it is C2H6, it's grand. So here we're going to write in C2H6, or my ethane, plus oxygen. So it'll be C2H6 plus oxygen to give me carbon dioxide plus water. Now my next step is to balance. So from what I've just written on the screen, that will get me a total of 4 marks out of 6. The formula for ethane is correct, oxygen is correct, carbon dioxide and water are all correct. And that gets you 1 mark for each correct formula. Now just remember, when you're going back to older exam papers, the marking of your balanced equations is different in the older papers. The marking was changed in 2024, where the chief examiner decided to give you marks for each correct individual formula. Prior to 2024, if you had one of those formulas incorrect, you lost all 6 marks. Even if you balanced correctly according to your numbers, it's wrong. So now, the examiner is trying to help you pick up more marks here, so they give you 4 for that. If one of your formulas was incorrect, take 1 mark off, and then you can't get your marks for balancing. So now I'm going to make a list of my elements in this table. We have the left-hand side of the equation and the right-hand side. And we have carbon, hydrogen, and oxygen as the three elements listed in that equation. When a chemical reaction happens, you have a certain number of atoms of each element in your molecules. And when you break your bonds and form bonds to form product, you have to have the same number of atoms of each element. So if you have a Lego tower that you smash apart and then you rebuild something new out of it, you have to have the same number of Lego bricks. So the same idea applies here. You have to have the same number of atoms of each element on each side, but you cannot mess with the little numbers. You can only change the numbers in front in the balanced equation. So here, let's make a list of all of our carbons. So for carbon, I have 2 carbons on the left-hand side. And on the right-hand side, we only have 1. The carbons are not balanced. We can't make a carbon atom disappear. So we're going to have to balance that in a minute. Now we go for the hydrogens. Hydrogen, you have 6 of them on the left-hand side. But on the right-hand side, there's only 2. Okay, my hydrogens are going to be a problem as well. For the oxygens, you have 2 oxygens on the left. And now look at the oxygens on the right. You have oxygen in 2 molecules. You have 2 oxygens in carbon dioxide plus 1 from your water. So 2 plus 1 is 3. Now, we need to balance, and I strongly recommend when it comes to combustion reactions, you balance in the order C, H, O. Always leave the oxygen till last, because if you look at your balanced equation here, your oxygen is in one place here. So it's going to be the easiest one to balance at the very end. So looking at my balanced equation, let's go for carbon first. I have 2 carbons on the left, but only 1 on the right. So I need to put a number in front of the CO2 that's going to balance my carbons. I'm going to put a 2 here. That 2 multiplies every atom or every element in carbon dioxide by 2. You had 1 carbon in carbon dioxide, times it by 2, which means I now have 2 atoms of carbon. So my carbons are balanced, but it also changes the number of oxygens. You have 2 times 2 is 4 for the oxygens, but we still have an oxygen over there on the right-hand side. So in total, you now have 5 atoms of oxygen. Why is that not going away? You have 4 plus 1 is equal to 5. And that's your total number of oxygen atoms on the right. Now, hydrogen is up next. What do we put in front of the H2O that's going to balance the hydrogen atoms? I would put a 3. 3 times 2 is 6, making it 6 atoms of hydrogen on each side. So the hydrogens are balanced, but it has now changed the oxygens. You still have 2 times 2 is 4, but now you have to add 3. So it's 4 plus 3 is equal to 7. There's a total of 7 atoms of oxygen on the right-hand side. Now to balance this, you've 7 oxygens on the right, but I only have 2 on the left. I need to put a number in front of the O2 that multiplies by 2 to give me 7. I would put 3.5. Now, I know some of you are absolutely allergic to using fractions and decimals here. That's fine. I would do it this way just because it's easier to balance it this way. And then by doing that, that gives me 7 atoms of oxygen on each side of that equation. So now I have written my balanced equation, and that gets me my last 2 marks. So now I would be at 6 out of 6. If your balancing is incorrect, if one of those orange numbers was incorrect, you can't get the final 2 marks for balancing because your balancing is incorrect. Right, let's have a look at the worked example in your notes, which I have just accidentally just done. So it's the balanced equation for the combustion of ethane. Now I'm going to change that. And instead of saying the balanced equation for ethane, I'm going to mix it up and say ethanol. Because this one did actually come up quite recently where they had to write the balanced equation for ethanol. Now, if you haven't done the alcohol topic yet, you might not know what the formula for ethanol is. Ethanol, so ethan means it has 2 carbon atoms, single bonds, and there's an alcohol functional group, which is an OH group. Then the rest of the atoms in this molecule, remember carbon has to have 4 bonds, they are all hydrogen atoms. Now the formula for ethanol, you can write it a few different ways. Some people prefer to write this formula as CH3 for this first part. Then you have CH2 for this bit here with an OH on the end. That's absolutely fine. Or you can write it as C2H5OH. Both of those formulas have the correct number of carbons, hydrogens, etc., and the functional group, the OH group, is shown. So that either of them are correct when you are writing this balanced equation. Now I'm just going to move the page up a tiny bit, just so that it's out of the way. So my formula for ethanol is C2H5OH. Now it's going to combust, so it's reacting with oxygen, and it forms carbon dioxide plus water. Now, when it comes to this, always draw your table for yourself. You can do it in your head. You're not getting marks for showing me the table of how you balanced. However, it helps to keep you on track here, particularly with the oxygens. So we have the left versus the right-hand side, and we have 3 elements, carbon, hydrogen, and oxygen. For the carbons, you have 2 carbons on the left-hand side, so these carbons here, and you have 1 on the right. Next, let's look at the hydrogens. You have 5 plus 1 is 6 on the left-hand side, and over on the right, you have 2 atoms of hydrogen. Then we move on to the oxygen. You have 1 oxygen in the ethanol plus 2 oxygens from the oxygen molecule. So I have 1 plus 2 is equal to 3 atoms of oxygen on the left. And on the right-hand side, you have oxygen here in the carbon dioxide. You have 2 of them plus 1 in water, which will be 2 plus 1 is equal to 3. Now we need to balance this. So let's go for the carbons first. I need to put some number in front of CO2 that's going to balance my carbon atoms. Now here, we're going to put a 2. 2 multiplies everything in carbon dioxide by 2. That gives me 2 carbons now on each side. So carbons are balanced, but it knocks out the balancing of my, oxygens. So 2 times 2 is 4 for the oxygens, plus 1 is 5. So you have 2 times 2 oxygens in the carbon dioxide, but you still have this oxygen over here on the right-hand side. Now, let's go for the hydrogens. You have 6 hydrogens on the left, but only 2 on the right. So I need to put a 3 in front of the water. That will give me 6 hydrogens on each side, but it also knocks out the balancing of the oxygens. So you have 2 times 2 is 4 from the carbon dioxide, plus 3 from the water. 4 plus 3 is equal to 7. Now, we have 7 oxygens on the right-hand side. We have to have 7 on the left. But the only number we're going to change is this number here in front of the O2. Leave the C2H5OH alone because you've already balanced your carbons and your hydrogens. Now, there's 1 oxygen there in the ethanol. So that's 1 of the 7. I have to multiply oxygen by some number to give me 6. Because if there's 1 already there, I need another 6 atoms to add together to give me 7. So I'm going to put a 3 in front of the O2. 3 times 2 is 6 plus 1 is 7, giving me 7 atoms of oxygen on each side of the equation. Now, while I've done that balanced equation for an alcohol, which is not actually a hydrocarbon, the same process or the same principle applies. You have something reacting with oxygen and you form carbon dioxide plus water, and then you have to have the same number of atoms of each element on each side of your equation. Now, I would recommend practicing that with a few different examples of hydrocarbons, for example. So I'm going to make a list of them. I would ask you to try out balancing ethane for yourself, ethene, propane, butane, and butene. or just I'll call it butene because but1 and butene would be the same in terms of the energy release because you've got the same types of bonds. And just if you can write your balanced equations for the combustion of those 5, there is literally nothing the examiner can throw at you that you won't be able to adapt and make it fit based on the balanced equation that's given to you in the question. Right, so up next, let's talk about the bomb calorimeter. So this idea that we're working out the heat of combustion, well, how do you know what the heat of combustion is? That's where the bomb calorimeter comes in. And it is used to measure the heat of combustion of a substance. And it's also used to measure the number of kilocalories in food. So when you look at a food label, the kilocalories that you see on a food label actually comes from someone put that food in a bomb calorimeter and literally set it on fire and looked at how much energy it released. Now, there's a definition here called the kilogram calorific value of a fuel. It's the heat energy released when 1 kilogram of the fuel is completely burned in excess oxygen. It's the kilogram calorific value of fuel. So it would be stick 1 kilogram of the food or the fuel inside the bomb calorimeter, set it on fire, and measure how much energy that 1 kilogram would release. Now, the kilogram calorific value of a fuel is useful when comparing the efficiency of different fuels. The higher the value, the better. We want fuel to have, if you have a fuel that's really, really light, if that light fuel emits loads of energy when it burns, that's the ideal scenario because it's light but has a high kilogram calorific value. That 1 kilogram of that fuel will release loads and loads and loads and loads of energy. So it's an efficient fuel. Now, when you're asked in the exam, now I'm going to mention this in relation to octane number. If you are ever asked, why is such and such a good fuel? Usually my go-to would be, it has a high octane number. Now, you are never going to be asked, why is something a good fuel if it has a rubbish octane number, because it won't be a good fuel. So if it ever asks you, why is, I don't know, ethene a good fuel? Well, it has a high octane number. I don't know what the octane number is. I don't need to know what the octane number is. But I know that it will have a high octane number because they wouldn't be asking you about it if it didn't. But another answer that you can give is the fuel has a high kilogram calorific value. Now, I find the wording of that a little bit more difficult to remember. However, it is a perfectly valid answer in the exam. So if we see the back of these Cocoa Pops, this is what the food label will look like. The energy tab or the energy line in the food label, you have 2 different units for the energy released. You have kilojoules and you have kilocalories. Now, where did those numbers come from? They literally came from someone putting the Cocoa Pops into a bomb calorimeter and setting it on fire. I used to do this experiment with my year 7s in the UK where we tried out different varieties of crisps and looked at which ones have the higher calorie content based on the amounts of energy a certain amount of that crisp released when you set it on fire. My lab stank for days afterwards. It was ridiculous. But anyway, so how does the bomb calorimeter work? Now, in your notes, there is a diagram for this, but to be honest with you, the most artistically gifted amongst us is not going to be able to recreate that diagram in the exam. So I'm going to give you a different diagram here on the screen that is a 2D diagram, and if you can draw 2 squares, you'll be fine. Now, for the bomb calorimeter and the explanation for how it works, this would be a maximum of 15 marks. And a diagram will be at least 3 of those marks. So we want to be able to show everything that needs to be shown, but there's 4 key points that we have to hit in our answer. So up first, I'm going to draw the bomb. It has a spectacular name when all it is a copper container. Now, into the bomb, you put a crucible, which is just a little metal dish. And the thing that you are going to burn goes into the crucible. But you need to know exactly how much stuff you put in the crucible. Because if you were to put 1 mole of glucose in there, for example, glucose has the formula C6H12O6. The mass that 1 mole of that would have is actually the relative molecular mass. So we would have 6 times 12 for the carbon, plus 12 times 1 for the hydrogen, plus 6 times 16 for the oxygen. That means the glucose that we would need to put in there would have a mass of 180 grams. So if I wanted to put exactly 1 mole of glucose in the crucible, I would need to put 180 grams of glucose, which is quite a lot. Sometimes the crucible is quite small though, and we don't want to overload it. So chances are, am I actually going to put 1 mole exactly inside the crucible? No. But as long as you know exactly what mass you put in that crucible, you can work out moles using your moles triangle from the moles topic. So, step 1, for part number 1, you're going to place a substance of known mass, and it's important that it is of known mass, in the crucible and place in the bomb. Perfect. Now, what the examiner is going to give you marks there is for indicating that you have known mass of something. Then you put the lid on the bomb and you feed the electrical cables through it into the substance that's going to be tested. Now, the purpose of the electrical cables is actually going to be to set it on fire. Then you lower the bomb into the calorimeter, which is just a fancy word for a container of water. Now, inside this container, you have a fixed mass of water, a fixed amount of water. Not overly important yet. Now, when this reaction happens, you're going to set the stuff in the crucible on fire. And because you're setting it on fire, it's combusting. Therefore, it is an exothermic reaction. So energy is actually going to be released from the thing inside the crucible to the surroundings. But in order for you to ensure that absolutely every part of that substance reacts, we need to ensure that there is enough oxygen inside the container. So what we do is we add, or you pump in, oxygen gas. So you add oxygen gas to the bomb under pressure. And what that does is it ensures there is enough oxygen for complete combustion of the thing in the crucible. You're ensuring that every single molecule of the thing you're testing is going to react with oxygen and form carbon dioxide and water. So you have the maximum amount of energy output from the thing as it burns. Next, you lower the bomb into the calorimeter. Now, and you ignite the sample using the electrical wires. If the substance, when it burns, is going to release energy to the surroundings, we want to figure out how much energy is being released. And that's why the bomb is made out of copper. Copper is a really good conductor. So the energy that's being absorbed by the copper from the combustion will then be transmitted to the water around it. So the water around the bomb actually gets warmer. But we need to know how much warmer does it get. So there has to be a thermometer placed inside the bomb calorimeter, like that. I know my diagram is fabulous. So my thermometer is then going to tell me what the energy change is, or what the temperature change is. Because this is a combustion reaction and energy is released to the surroundings, the temperature on the thermometer should increase because it's exothermic. Now, you record, before you ignite the sample, you record T1, which is the temperature at the start, before ignition. And then, once you've done the reaction and all of your substance has combusted, you record T2. And T2 is the final temperature. It's the highest temperature measured on your thermometer. Now, you need to work out what the change in temperature is in order to work out what the heat released from the substance being burned is. Now, this next bit down here, my last bullet point for how the bomb calorimeter works would be the formula that we use to work out the heat released. So your heat released is equal to the mass of what's inside the calorimeter multiplied by the specific heat capacity. Now, the specific heat capacity is the heat capacity of water. I know those of you doing physics will use different values, but in chemistry, we only use water here. Multiplied by delta T. Now, for physics, if you use a different symbol to H, I don't care. As long as you are working out the heat released and you have the correct number here, it's fine. So M, this is the mass of the thing in the crucible. So it's the mass of the combusting material. And the mass will have to be in kilograms. And the reason why is because of the specific heat capacity. You'll be given the specific heat capacity of water as 4.2. The unit is kilojoules per kilogram per Kelvin. So because of the per Kelvin component of the specific heat capacity, your mass has to be in kilograms. It can't be in grams. Now, that will be given to you in the exam. Don't learn off that number unless you're like me and I forget to always give it in tests. But anyway, so it will be given to you. Don't worry about that. Now, the delta T is T2 minus T1. Technically, your temperature here can be in degrees Celsius or in Kelvin. It doesn't matter. So if, for example, the starting temperature T1 that was inside the water bath at the beginning, so say, for example, T1 was 20 degrees Celsius. And then after you've done the experiment, T2 is 80 degrees. To work out your delta T, it would be 80 minus 20, which is equal to 60. Now, the difference in temperature here, whether it's in degrees Celsius or Kelvin, is the same. If I was to put both of those into Kelvin and then subtract them, you add 273 to both of them. So 80 plus 273 is 353. Minus 20 plus 273 is 293. Why did I even type that in? Then 353 minus 293 on my calculator is equal to 60. So if you're given T1 and T2 in the exam, you'll need this for your heat of neutralization experiment. Just subtract them. Whether it's in degrees Celsius or Kelvin, the difference will be the same for both units. And that is your heat released. So that will work out how much heat is released from the substance inside the crucible to the surroundings. Now, if you know the mass of what's inside that crucible, well, then you can work it up and figure out how much energy 1 mole of that substance would release. And that's how we would then use it. So that is how the bomb calorimeter works. Now, as you can see from my answer, I'm not writing a massive essay here because you don't need it. 9 times out of 10 in the exam, the examiner comes at a bomb calorimeter with name the piece of equipment used to measure the heat of combustion. And you just need to write bomb calorimeter and we get 3 marks and move on. Or another thing would be give a use for a bomb calorimeter and you need to say it measures the heat of combustion. And then we move on. This idea of explaining how it works, it links into the heat of neutralization experiment. And to be honest, it's a very similar experiment, except we won't be using the bomb calorimeter itself. We're going to do something a little bit different. But if you understand what's happening here, you're not going to have any problem with the heat of neutralization experiment because it's the same overall idea of what's happening in both of those 2 different topics. But I would take a little bit of time just to go through this. To be honest, if you have a properly labeled diagram, I would then use a properly labeled diagram to kind of flesh out my answer. So other labels that I would put on this, we have the bomb, we have the calorimeter filled with a known volume of water, then you have your thermometer and you have your electrical wires. And then we have our sample being tested. And technically we should also mention about the oxygen under pressure as well, to ensure the complete combustion of what's inside the crucible, but it's not essential, not in the diagram. Right, that is it for the bomb calorimeter and heat of combustion. Now, this isn't the last we're going to see of heat of combustion. In a few lessons' time, we're going to look at how do we actually calculate how much energy is released during a combustion reaction. Okay, and I'll see you then.